Hello everyone, this is Professor Ma and this is the introductions on the sections on gradient in the directional derivatives. We have partial derivatives and for example at a point P on a surface, here's the pictures and the P is ABC and we put the partial derivative respect to X and that means we're going to set the number b a constant in a plane is a plane y go to b, and we cut across and we look at the curve on the plane and y to b, and then we partial f respect to x is the slope of this guy. Slope. And so here's the pictures. And of course, in the then partial y is this, if I were to take a plane that cuts in the y directions in this manner, so I have a curve on the surface like that, and in the y direction there will be the slope of that line, and that will be the partial y. Now, assume that we have a compass. Okay, so I'm going to graph my x, y, z directions, and it's oriented in this manner. And here's the x, here's the y. So now assume underneath the point P, here's a compass, and in particular on the compass there's a directional vectors. What I mean by directional vector means the length of this is 1. It just tells you the direction. So you have a compass. It's fixed on the compass, length 1, needles pointing in that direction. Unitized. If you have any other vectors in pointing same direction, you need to unitize it to become the directional compass directional vectors. Okay. And that direction defines a plane. That plane cuts the surface, and that surface has a curve with a cross sections with whatever this sphere is or semi-sphere, and that has a slope. So instead of just the partial x, partial y in the x, y direction, now we want the slope in a particular directions, in any directions on the compass. It turns out the answer for doing this is very easy. Okay, and so the slope in that directions, the compass directions, direction vector u, we call that the directional derivatives in the direction of u. Okay. And the directional derivative, it tells you a little bit more than just the slope. It actually tells you, you actually have a sign, that is a signed slope. And if the derivative, the directional derivative is possible, we're going to calculate that. And if this calculation will come out positive, that means the directions you're going is going up. And if the directional derivative is negative, it means that on the surface you're going down. So in other words, if I traditionally have a slope equal to, let's say slope equal to 1, but in directional derivative, in that direction where slope is positive 1, but in opposite direction, because going downwards, the slope is minus 1. Okay, so this is a sine slope, and the directional derivative we calculated give the sine slope. And how do we get that? It's simple. You form this partial x, partial y. This number is slope m and l, and you form these vectors, and these vectors call the gradient, and then the sine slope. Oh, by the way, this gradient is denoted by this little triangle shape, and this particular is called del f. Del f is a gradient at f. And then you write down which point you are interested in, point A, B. Okay. And the directional derivative is just a del dot with the directions. Okay, you make this so in other words, this is important numbers. You started with a different compass direction u, that then upstairs at the point, it gives you the slope of the cross-sectional curve in the direction of u and give you the slope in that directions. Okay. And here's the calculations. By the way, again, we use a sphere. That's easy to do, and so this is a sphere. Well, let me calculate through, show the calculation, then we will draw it out. And this is spheres of radius 7, and this is the partial with respect to x and y. So the gradient is, m is this, l is that. So gradient is minus 1/2, minus 1/3. Okay, and that's a very useful vectors. Okay, so in the direction, so here's the pictures. Okay, so we calculate the at that point the gradients. Okay, if I put this as if I if I put the x y axis over here, if this put this x shape of x y. So the gradient is pointing at x y. Well, I have to be careful. Minus 1, minus 1/2, minus 1/3. So the directions. Oh, sorry, that's not the gradient. That's the u. Okay. The gradient pointing something else. The gradient pointing at minus 1/2, minus 1/3 is pointing in that direction. So it's not in this picture. But this is the directional vector u. Sorry, my mistakes. Oh God, this is not a gradient. I want to know the slope in that directions, and so you just dot it with the gradients, and therefore the sine slope in the directions u is minus 1/5. Okay. And here's another calculations of calculating the directional slope. The directional, okay, the only things over here you go through, you calculate the gradient, so you get a gradient it is equal to these factors. And the part B, it says find the directional derivative in these directions. U. You have to take that, unitize it. Okay, that's just a directions. Go back to with specific directions, but that is not the directional vector in that directions. You have to unitize that, and then you dot with the unit vector, the unit derivatives in that directions is equal to root 1/5 is the unitized vector. These are the unitized vectors of unit direction. So that's gives with dot with that you get the directional vectors, directional derivatives. And this is a general gradient formula with x and y, whatever x is, y is. Okay. What an important fact about gradients. And if the gradient is 0, that's what we have in the maximum and saddle points. That's basically saying the partial x is 0, partial y is 0. That means you either are critical points. So this is just another way of saying the things we back in 3 sections ago about. Oh no, we haven't got. This is the things we're going to do 2 or 3 sections now, in the next section, in fact, and how can we tell we are on high point and low points or on the saddle points? That's when the gradient vanish. We're going to do that later. Okay, so this is an important observation. This is the identical formula for 1 dimension is derivative at prime 0. Now in the 2 dimensions over here, a surface is a gradient equal to 0 to give you the maximum. The second thing is, since these in the directions of u, so u, suppose u is directional vector, and then del f dot of u is equal to the directional derivative. The directional slope, if you like. And then the question is, okay, when is this the biggest, largest, the max? Okay. The larger it is, the steeper the line is. That is the directions of the steepest ascent, assuming it's positive. Okay. So where is this number u? That's the maximum. Well, these, if you think about it, the vector that dotted with ml, that will give you the largest is the unitized. It's in the same, it has to be in the same directions, coincide. That's when you dotted with, you get the most amount. When the vector dotted with itself, it's the, it gives you the norm. And if the length is 1, then the one that you want to dot to give as much as possible is a unitized gradient. So in other words, the gradient is the directions of maximum ascent. Okay. Let's see. Steepest climb. The opposite direction gives you the steepest drop. All this happening on the tangent plane. Okay. So here is a picture. Suppose I have a plane, and here how that plane is made. If I take a pole that's m meters high, and this is 1 unit from here to here, and I take another pole that's L meters high, and again it's 1 meters out. Both of these are 1 meters out, and that make a little plane, and that extend this plane to these entire things, and then ask the question: which direction is the steepest climb? If I were to stand over here, I'm ready to go up. Where is the steepest? Well, it turns out the steepest is this. You take M, put on a 4, you take L, and put over here. That's in these directions. Okay. The directions of the gradient. Okay, so in this case, then the steepest direction is 1/2, 1/4, 1/2. And here is the problems, and you can draw the gradients, and in particular, this is the gradient on the surface of a sphere. If you're on a sphere, and you say, where's the steepest climb? Oh, it's easy. That's where the pole of the sphere is. That's the steepest climb. And this calculation shows you that actually, yes, you do get that gradient pointing in the center of the sphere. And since the directions of level curves, the slope is 0, so that means the gradient dotted with the directions that the level curve is must be 0, because it's supposed to give you the slope in that direction. If it's level curve, then directions on the surface, you're not gaining any height, so the slope is 0. But that number slope is supposed to be dot product between gradients in the directions of the path of the level curve. Okay, so that means the directions of the gradient starting to become 0 means it's perpendicular. So the gradient always perpendicular to the level curve. And that's interesting. Okay. Yeah, that's the importance of the gradient. And bye-bye, and talk to you next time. See you later. Bye bye.